How was your weekend, Professor?
It was good. It was Mother's Day, so I visited my parents. We had a nice dinner. Our first time going out to a restaurant ever since the pandemic began. Because my sister just recently got vaccinated, so before that she wasn't comfortable going out, but now she's vaccinated, so we went out to a restaurant. So it was nice. How about yours?
It was good. I cooked my mom some lunch.
Nice. It's great. Nothing like a home cooked meal. I think that's always the best way to show love.
Quick question for you, if it's all right.
Sure.
When I emailed you that that heat convection coefficient, was
Yep.
that correct?
Oh shoot! Yeah, I remember seeing that email, but I forgot to respond. Let me take a look at it again after the lecture today, and then I'll get back to you on that. Yeah,
All right,
sorry about
thank
that.
you.
It kind of slipped my mind over the weekend. Yeah.
That's all good.
Okay, it's 2:30, so let's go ahead and get started. All right, so good afternoon, everyone. How's everyone doing today?
Good.
Good, good. All right, it's our last week together, and so we have the lecture today, and today's the last day. We'll be covering any new content, and then Wednesday we'll be doing our review for the final. Okay, so after the class today, I'm going to put a poll onto the Canvas site where you can vote on the topics that you want to see on Wednesday, right? And let me just remind you guys what day our final is, because that's going to be the most pressing thing. I think we talked about it here. Nope, maybe not. Maybe on the previous day. Yep, final exam. So final exam is going to be next Wednesday. So that's going to be May 19th. And it's going to be from 3 p.m. to 4:50. But usually that 10 minutes is there just to have you transition in between different rooms. And so instead of being 4:50, we'll have the final exam take place for the full 2 hours. And so 3 p.m. to 5 p.m. Okay, so let me write down that information on our newest set of notes. Okay, so it'll be a 2-hour exam. Okay, and we'll take it in the same format that we usually do, for our midterm exams. And so I'll open up a quiz on Canvas, and then you'll just take it there. Okay, I'll open up the Zoom room just so you can come in and ask questions if you want, but that part is optional, right? All right, so the format for the final exam, because we do have a little bit more time than usual. I will make the final exam a little bit longer than our midterms. Okay. And so usually for our midterm exams, we have 3 conceptual questions. And so for the final exam, there's going to be 4. Okay, so just add one more there. Okay. And then I'm going to add one more problem solving question as well. And so there's going to be 3 problem solving questions. Okay. And that number actually works out perfectly because we've covered 3 big units in this class, and so you can expect out of the 3 problem-solving questions, there's going to be 1 question on conduction, right, which was the stuff we covered on the first midterm, 1 question on convection, okay, and 1 question on radiation, which is the stuff we're covering right now. Okay. And so that's the breakdown you can kind of expect. Yeah. So the final is cumulative. Yeah. So it's going to cover up to the stuff we learned in the beginning, but remember, it's not absolutely everything. And so I trimmed a lot of the topics just to make your study more efficient. And so before you start studying, don't just start reading the lecture notes. Look at the study guide that I posted online, and so the study guide will tell you. That will tell you the list of topics and the list of things that I'm going to expect you to know for the final. And I've trimmed about maybe 5 or 6 weeks worth of content from the, overall, because we've had 15 weeks of class, and studying 15 weeks of stuff is madness. I think that's way too much. And so I've trimmed about 5 or 6 weeks worth of content from there. And so, make sure you look at that study guide as you start to study, so you don't study things that aren't going to be on the final. Okay. And for the conceptual questions, you can expect a similar breakdown. And so, it should be roughly, the same breakdown between conduction, convection, and radiation. But there, you can expect 1 extra question on radiation for the conceptual short answer, right? Because that's kind of the stuff I haven't tested you on yet. So for the short answer, you can expect 1 question on conduction, 1 question on convection, and 2 conceptual questions on radiation. Okay. And so it's a pretty balanced exam. I think the numbers kind of work out well for that, except it's very slightly skewed more towards radiation, just because that's kind of the new stuff that we're going to look at. Okay. And I'll remind you of this on Wednesday too before we review. But I just wanted to give you the heads up, and because I'm starting to write the exam, and so it's probably I'll finish writing it by the end of this week. Okay. All right. So any questions on any of this, the final exam, or just anything that we've been covering so far? Okay. All right. So let's go ahead and continue where we left off. All right. And today we're finally going to finish up radiation exchange. Okay. All right. And so radiation exchange, remember what this refers to is the exchange of heat or the transfer of heat between 2 surfaces via radiation. Final date. So the final date is going to be next Wednesday. Next Wednesday, May 19th. Yeah. Right here. Right. Okay. Radiation exchange. So this is the exchange of heat via radiation between 2 surfaces. Right. And what we learned last time was that we can take a kind of a very similar kind of thermal circuits approach to this radiation. Okay. Those thermal circuits is something that we've been using all throughout this class, and it's been super useful. Okay. Good. Because it's radiation, we have to modify our approach a little bit, and so it's not going to be, the resistances are going to have very different values, and also the nodal values will have different values as well. Okay. And so in terms of thermal circuits, there's basically 2 different types of resistances that we can have, right? And so the first type of resistance has to do with the fact that that different surfaces might not radiate over all the different ones, or in other words, this is our view factor resistance. Okay. Okay. And the view factor resistance, remember, was given as a product of the view factor, okay, times the area all over all this raised to the -1 power. Okay. And so view factor resistance is always going to be here. Okay. Because no matter what, as long as the two surfaces are separated from each other, there's going to be some resistance from the fact that not all the radiation is going to hit, right? The only way that view factor resistance is not going to be factored is if your two surfaces are basically right next to each other. No social distancing or anything like there. Okay. In that case, if the two surfaces are right on top of each other, then 100% of the radiation is going to go from one surface to the other because they're right on top of each other. Okay. But in most cases that's not the case, because that's not really an interesting thermal situation, at least in terms of radiation. And so you're always going to have some degree of separation. Okay. All right. And so the other resistance that we usually have is known as the gray body resistance. Okay. And gray body resistance, this has to do with the fact that not all surfaces are perfect emitters of radiation. Okay. And remember, we have this parameter that we have for our radiation known as epsilon, right? So this is the emissivity. Okay. And it's a number between 0 and 1, and it rates how well the surface is at emitting radiation. Okay. And so if epsilon's closer to 1, that means it's a much better emitter of radiation. Okay. So that it acts like a black body. But if the emissivity is closer to 0, that means the surface is kind of crappy at emitting radiation. Okay. And so the gray body resistance is given by 1 minus epsilon all over epsilon times A. Okay. Okay. And of course, because this is called the gray body resistance, we only account for this whenever we have gray bodies. Okay. All right. And so what's the goal, right? And so whenever I give you kind of a radiation exchange problem, the goal is more or less kind of always the same thing, right? And so the goal for most radiation exchange problems is to solve for the radiosity values. Okay. And so these are the J values, okay? And the way you're going to solve for the J values is you're going to use a linear system of equations. Okay. And the way that you obtain that linear system of equations is through the thermal circuit. Okay. I think where we left off last Wednesday was we were kind of right in the middle of an example going over that. Okay. Okay. And so any questions on this so far? Okay. And so let's go ahead and pick up where we left off on that last example then. Okay. Right. And so in this example, we have concentric cylinders. Okay. Both of which are gray bodies. Okay. And so our two cylinders look like this. And so we'll call the inner surface, we'll call the inner cylinder surface 1. And we'll call the outer cylinder surface 2. Okay. Right. And so the circuit between these two guys is, we need to account for both the view factor resistance and also the gray surface resistance for both the surfaces. Okay. Okay. And so our circuit looks like the following. Okay. right? So we have 3 resistors, the ones that are listed up there, okay? On the one hand, on the one side of the circuit, we're gonna have surface 1, and our other side, we're gonna have surface 2, right? Right. And remember, the ends of the circuit, we always use the black body emission, right? And so it's gonna be sigma times the temperature raised to the 4th power, okay? All right. And so in between them, let's go ahead and write the view factor resistance, right? And so this is gonna be 1 over J1, or sorry, 1 over F12 A1, okay? And so that's the fact that, you know, these two surfaces are separated, and so there's going to be some view factor resistance in between them, okay? Okay, and then we have the 2 gray body resistances for the 2 surfaces, right? Okay.
They're both, there's air in them, or are they like bunch up to each other?
They're
Oh, together. Never mind. Sorry.
yeah, they're separated, and so we're going to assume that there's vacuum between them, and so there's no conduction or convection in between. Yeah, so
Okay.
we're just assuming radiation. All right. And remember, the things that we're solving for in these problems are usually these radiosity values. Okay, so we have J1, J2 here. Okay, and so you always put the radiosity values right after the gray body resistance. Okay, and so we're going to solve for this and this. Okay. Right. And so the way that we solve for these two is that since we have 2 unknowns here, we're going to need 2 equations. And remember, the way that we obtain these equations is we take this circuit and we sum up all of the heat going into the J nodes, okay? Okay. And so let me, just because I want to make sure we get through everything, I'm going to go through this a little bit quickly. But let me show you how to do the J1 node, okay? All right. And so into the J1 node, we have 1 source coming in, okay? And so coming in, we have the heat that's coming from, that's crossing over the gray body resistance, okay? And so this one's going to be sigma T1 to the 4th divided by 1 minus epsilon 1 divided by epsilon 1 A1, okay? Sigma T1 to the 4th power minus J1, sorry, okay? And so remember, the way that you compute a heat transfer in a circuit is you take a difference in between the nodal values. And so here we take a difference between sigma T1 to the 4th minus J1, because those are our values at the nodes, and we divide by the resistance in between them, okay? Okay, so that's all the heat coming in, and then coming out, we have the heat that passes from J1 to J2, okay? And so we have J1 minus J2 divided by the resistance in between them. So it's going to be 1 divided by F12 A1, okay? Okay. And so you should have everything that you need in this formula, because in the problem I give you the temperatures of the surfaces, and you should have T1, okay? I give you the emissivity, so you know that too. You can compute the areas and the view factors, and you're going to have one equation for where J1 and J2 are still unknown, okay? And so if you plug in all the numbers for that, you're going to end up with an algebraic equation that I'll show you on the next page, okay? Okay, so any questions on this? Okay, all right, so let's go ahead and plug in the numbers. Okay, and so we plug in the numbers, what we get is 9234.17 is equal to 1.57J1 minus 0.314J2. Okay, and so that's one equation. Okay, and so this equation 1. Okay, all right. And so we're going to find the second equation by summing up all the heats going into the J2 node. Okay, and so if we do all that, we plug in the numbers, we end up with an equation that looks like this. Okay, so you have 2128.04 is equal to 1.78 J2 minus 0.314 J1. Okay, and this is going to be our equation 2. And so now what we have here are two equations that we can solve for our two unknowns, J1 and J2, okay? All right, and so you can solve this equation. There's, probably up to this point, you've seen that there's a million and one ways to solve a linear system of equations, okay? And so one way that you can do this is you can just plug these into your calculator, into your graphic calculator and do it that way, right? If you know how to do this with MATLAB, you can do it with MATLAB. But just for the sake of, of transparency, I'm going to show you how to solve this by hand. Okay, and so since this is kind of just a 2x2 system, we can solve this by just basically substituting and solving and substituting. Okay, all right. And so what I'm going to do is I'm going to take equation 1. Okay, and I'm going to solve it for J2. And so basically, I'm going to isolate this such that J2 is isolated. Okay, and so if we move this minus 1.57 J1, we move it to the other side, and then we divide the whole thing by negative 0.314. Then what we get is the following: so we have J2 is equal to 1 divided by 0.314 times quantity 1.57 J1 minus 9234.17. Okay, and we can divide through by this, and what we get is J2 is equal to 5J1 minus 29408.185. Okay, right. And so this isn't complete yet, because we have J2 in terms of J1. But what we can do is we can take this J2 and plug it in to equation 2. Okay, right, and then what that will do is that will eliminate J2 from our second equation and allow us to solve for J1. Okay, all right, and so we do that, and so we plug into equation 2. What we get is 2128.04 is equal to 1.78 times 5J1 minus 29408.185, okay, minus 0.314 J2, or J1, sorry, okay. Right. And now what we have is something we can work with, because now that we've eliminated J2 from the second equation, we can just take this equation and solve for J1. Okay, because J1 is the only unknown left in this equation, and so we can just outright solve for it. Okay, and so if we do that, we work through kind of the algebra a little bit. We get J1 is equal to 6344.59 watts per meter square. Okay, and so that's one radiosity down. Okay, and so now we just have to solve for the other one. Okay, and that's easy because we have this expression up here for J2, right? And so now that we have J1, we just plug J1 into there and solve for J2. Okay. Okay. So any questions on this? Okay. And so let's go ahead and plug in for that and solve for J2. Okay. And so we solve for J2, and what we get is J2 is equal to 2314.74 watts per meter square. Okay. And now at this point in the problem, we've solved our linear system equations and we have our radiosities. Okay. And so now what we can do is we can take the radiosities and solve for the radiation exchange. Okay. And so the radiation exchange in this case will be Q12 is equal to A1 F12 times J1 minus J2. Okay. And what we get from this is 1266.04 watts. Okay. Right. And so once you have the radiation or the radiosities, you just plug that back into here and you solve for the actual amount of heat transfer or the radiation exchange between the surfaces. Okay. All right, and so that'll do it for that example. And so are there any questions on this? Okay, and so let's do one more example because I think these problems helps to look at more. Yeah. Oh, Pedro, do you have a question?
Yeah, I have a question. Why do we use A1 instead of A2?
Yeah, you can use either one actually. And so remember, we have this reciprocal relationship where if you're going to use A1, then the view factor has to be F12, right? And so the area that you use has to match kind of the first number of your view factor. But if you wanted to use F21, you can use A2. Right? And so either of these would work. It's just that the area that you use has to match the same, the first one of your view factor. Yeah.
Okay, thank you.
Yep. Mm-hmm. All right, any other questions on this before we do another example? Okay. Oh. Okay. And so let's do an example that's a little bit more complicated and one that's a bit more consistent with your homeworks. All right, and so let's consider a case where we have two parallel plates and they're exchanging heat by radiation, not only with each other, but with the kind of the environment around it. Okay. Okay. And so let me draw the figure here. Okay. And so we'll call this surface down here surface 1. And we're going to have another plate up here. We'll call this surface 2. Okay. Right. And so in between them, we're going to say that there's a distance of 1 meter, and we'll call that distance big H. Okay. Let me list out the thermal properties here. Okay. And we'll say that T1 here is 800 Kelvin. And we'll say that epsilon 1 here is equal to 0.8. Okay. And then surface 2, the thermal properties are T2 is going to be equal to 600 Kelvin. And then epsilon 2 is equal to 0.6. Okay. Okay. In addition to that, since we don't have a closed system here, and so we don't, it's not totally enclosed by by all the surfaces, we have to kind of draw our own enclosure. Okay. So let me draw kind of another surface here. And since they both lead to the same place, I'm just going to call both of these surfaces, we'll count them as one. And so we'll count them as kind of surface infinity here. Okay. Right. And for the environment, what we'll say is that T infinity is going to be equal to 300K. Right. And we'll assume that we have a black body out for the ambient conditions. Okay. And so we'll say that epsilon infinity is equal to 1. Okay. All right. And so a little bit more complicated than our last example, because now we have 3 surfaces instead of 2. Okay. And so that's going to complicate our math a little bit. But what you'll see is that we'll follow just the exact same process that we did before. Okay. But the way what we're going to solve for in this problem is we're going to solve for the radiosities of the 2 plates. Okay. And so we're going to solve for J1, J2. Right. And then we're also going to solve for the heat transfer from these plates to the environment. Okay. Right. And so kind of one step builds into another one. And I'll write down the formal objectives of this problem on the next page. But before I do that, are there any questions on the problem setup and the diagram here? Okay. All right. So let's go ahead and write down the objectives of the problem. Okay. So we want to find. Okay. We want to find the radiosities of the 2 plates. Okay, so that's going to be J1, J2. And the other thing we're going to need to find here is the heat transfer to the environment. Okay. All right, and so even though we have one more surface here, we can go about this kind of the same way. And so we're going to start by drawing our thermal circuit. Okay, and here we have three end nodes. Okay. Right, and so I know this is not super matching up with the diagram, but just for the sake of space, I'm going to draw it like this, right? And so we'll call this down here, we'll call it node 1, okay? We'll call this node up top here node 2, and then we'll call this node here node infinity, okay? And just like we did in the first example, since for the end nodes, we're going to make them equal to the black body radiation for those surfaces, okay? Okay. And so up top, we have sigma T2 to the 4th. On the bottom, we have sigma T1 to the 4th. And then on the right, we have sigma T infinity to the 4th. Okay. Okay. And so the way we're going to do these is, we have to start with the gray body radiation, or gray body resistance for each surface. Okay. Okay. Even though the environment, is not a gray body, we can draw a gray body resistance for it anyway. Okay. Okay. Actually, let me use a different color here just to kind of illustrate that. So let's make this orange. Okay, gray body resistances. right? And our gray body resistances all have the same expression, but with different numbers in them, obviously. Okay. Okay. And so we have to account for those, okay? And so that should always be the first step when you draw your thermal circuits, is to write out your gray body resistances, okay? And then right after the gray body resistances, we're going to have all of our radiosity values, okay? Right. And then after we write out our radiosity values, we have to connect every single one of them to all the other ones, okay? Okay. And the way that we're going to do this is we're going to connect them with a view factor resistance, okay? Okay. And so, in this case where we have 3 different radiosities, we're going to have, each radiosity node is going to have 2 neighboring resistances. Okay. All right. Okay. Right. And so those are all of our view factor resistances there. Okay. And so the view factor resistance is going to be, the view factor in between those 2 surfaces multiplied by one of the areas. Okay. And remember, these view factor resistances, you can interchange them. So you can either use, these ones, or you can, do the reciprocal one with the other area. Okay. Okay. And so that's a thermal circuit setup. And so if I had to rate, most of the steps here to this, to these kinds of radiation exchange problems, this step where we write out the circuit, this is probably the most important one, because this is the one that kind of sets you up for everything. Okay. Okay. So any questions on this so far? Okay. All right. And so, when you're doing these problems, really spend a good amount of time drawing your thermal circuit, because that's going to set you up well for everything. Okay. All right. So before moving on, there's one more thing that we can compute. Okay. Okay. And that's the fact that our surface infinity here has an epsilon of 1. Okay. And so since our environment here is a black body, we can just straight up calculate J infinity. Okay. And so if your surface is a black body, then what you can say is the radiosity is going to be directly equal to your black body radiation. Okay. Because look at this equation here for the resistance, right? And so the resistance is equal to 1 minus epsilon divided by epsilon times A, right? And so if epsilon is equal to 1, this resistance is equal to 0. And so it's like this resistance isn't even here, right? And so if that resistance isn't there, then J infinity has to equal to the black body radiation, okay? And we can plug straight in for this because we have all of the all the numbers for it. And what we get is J infinity is equal to 459.27 watts per meter square. Right? And so that's one of the radiosities already straight away solved for you, okay? And so the only ones we have to solve for left are J1 and J2, okay? Okay, so any questions on this so far?
Will we see a problem where it's not a black body, so we can't cancel out the J infinity?
You might. And so, I think on the homework, I think I do give you a system of 3 different unknowns, or maybe I don't. I don't remember.
My
Uh,
other my
oh,
other
go ahead.
question is that if it's like that, then can we? I think in circuits there's a way to like you connect the center, you make another circuit within it to connect the two, so you can make simplify or something like that.
Yeah, yeah. And actually, for this case, you can basically simplify the circuit. So instead of a J infinity right here and this resistor, since this resistor is not here, what you can say is that this node right here is going to be sigma T infinity to the 4th, right? Because no resistor is basically saying that nothing is there. And so now our simplified circuit has 1 less resistance to worry about. Yeah.
Okay.
Yeah. But for the
Okay.
purposes of the exam, I'm never going to give you a system with more than 2 unknowns, because that's a little bit cruel. And I think you spend more time solving the math problem than you do the heat transfer problem, which is what I don't want for this class. Okay. Okay. Any other questions on this before we move on? Okay. All right. And so what we have here is we have 2 more unknowns. So we have J1 and J2, and so we know that we're going to need to have 2 equations for those guys. Okay. Okay. And remember, the way that we obtain these equations is we simply sum up all the heats that are going into those nodes. Okay. And so let's start with the J1 node. Okay. Right. And so this is a little bit more complicated than our last one because we have kind of multiple paths here. Okay. And so coming into the J1 node, we have the one that's coming in from sigma T1 to the 4th. Okay. Right. And so coming in, what we have is sigma T1 to the 4th minus J1 divided by the gray body resistance in between them. Okay. Okay. And so these are all the heats coming in. Okay. And on the right side of this equation is going to be all the heats going out. Okay. All right. And so going out, what we have is first we have the heat transfer that goes from J1 over to node infinity here. Okay. And so this is going to be J1 minus sigma T infinity to the 4th, all divided by 1 over A1 F1 infinity. Okay. Plus, then we have the heat transfer that goes between J1 and J2, right? And so that's going to be J1 minus J2 over R12. So J1 minus J2 all over 1 over A1 F12. Okay. Right. And so that's all of the that's everything for node 1 here. And so that's our first equation. Okay. And you can see here that everything that's unknown here is going to be J1 or J2, okay? Because everything else we can solve for outside of this. Right. And then for J2, we're going to have a very similar equation, okay? And so I'm just going to write this down quickly, but you can verify and see that the way I obtained this was the exact same way as up there. Okay. Right, so coming in, we have something from the sigma T2 to the 4th node. Okay. Right. And then we have going out, we have 2 contributions one between J2 and J1, and another between J2 and J infinity, basically. Okay. All right, and so we have our two equations and two unknowns here. Okay. Right. And so all we have to do here is plug in all the numbers for this and solve for J1, J2. Okay. The only problem here is that we don't know what these view factors are. Okay. And so in order to complete these equations, and actually solve them, we need to compute the view factors. And the way that we're going to do this is a combination of, looking up values in a table. Okay, along with our view factor rules. Okay. Remember, we have two rules, and so we have the reciprocal rule as well as the summation rule. Right. All right. And so let's start with F12 because we can look that one up in the book. Okay? And in fact, this is one that we've seen before, okay? Because this is going to be the view factor between two parallel plates. Okay. And then once we have F12, then the rest of the view factors kind of fall in line from there. Okay. So any questions on this so far? Okay. And so let's go back in the notes from before and find out what the formula for this view factor is. Okay. Right, so I think this is from table 12.2. Okay. For two parallel plates, their view factor Fij is going to be equal to Wi plus Wj squared plus 4 right, all of that raised to the 1/2 power, okay, minus Wj minus Wi squared plus 4 raised to the 1/2 power, okay, all divided by 2Wi, right, where Wi is equal to the length of the plate divided by length of plate 1 divided by the distance in between them, which for this case is just 1. Okay. And Wj in this case is the length of the other plate divided by the distance in between them. Okay. And so in that case, this is also 1. Okay. Right. And so if you plug in those numbers, what you get is F12 is equal to 0.414. All right. And so, we have one view factor here that we found from a formula, and that's usually all that you need. And so you usually just need one formula to find one view factor, and then the rest kind of fall in line from there. Okay. Because the next thing that we're going to observe is that both all the surfaces here are they're not concave. Okay. And so what that means is that there's no way for these surfaces to radiate itself. And so in other words, all the self view factors are going to be 0. Okay, so F11 is equal to 0, F22 is equal to 0, and F infinity is going to be equal to 0. Okay. Right. Well, I guess that's not, that last one's not true because, you know, we're combining the last two surfaces. We're combining all the environmental surfaces together. And so that last one's not true, but we also don't need it for this one. But F11 and F22 are going to be 0 because they're just single surfaces and there's no way for them to radiate themselves. All right, and so the rest of the view factors we're just going to find just by applying the summation and reciprocal rules, right? And then once we do that, we can plug in and get our equations for J1 and J2, and then finish up this this problem. Okay. Okay. So any questions on this? Okay. All right. And so first, let's find F21. Okay. And so for this, we're going to use the reciprocal rule. Right. And so for this, we're going to say that F21 is going to be equal to A1 divided by A2 times F12, okay? Where F12 is the view factor that we just found on the previous page, okay? And since A1 is equal to A2, since they are identical surfaces, right? What we get is F21 is equal to 0.414. Okay, so they have the exact same view factor, which makes sense because they're the exact same surface. Okay, or they're the same surface, just separated by a distance. Okay. All right, and now let's solve for F1 infinity. Okay, and for this we're going to use the summation rule. Which says that F1 infinity is equal to 1 minus F11 minus F12, okay? And since we know that F11 is equal to 0, what we can say is that F1 infinity is equal to 0.586, okay? And then similarly, we can do the same thing for F2 infinity, so we can use a summation rule, okay? Right, and so F2 infinity is going to be 1 minus F21 minus F22, right? And since F22 is equal to 0, then what we get is F2 infinity is equal to 0.586, right? Right? And so now that we have all the view factors and we have everything else in the problem, what we can do is we can take these view factors, plug it into these two equations, and then get a numerical equation for J1 and numerical equation for J2. Okay. Okay. So any questions on this? Right. And so let's go ahead and plug all those numbers in. Okay. And so for equation 1, what we're going to get is 93166.41. This is equal to 5J1 minus 0.414 J2. Okay. Right. And so that's our first equation. And our second equation is going to be 11291.61 is equal to 2.5 J2 minus 0.414 J1. Right? All right. And so now that we have these two equations and two unknowns, we can go ahead and solve them, okay? And so you can use your favorite way of solving equations. And so you can use your graphing calculator. You can use the plug and substitute approach that I showed last time, okay? And so just for the sake of time, I'm not going to go through all the work to showing how to compute these, but I'm just going to jump straight to the answer. But just know at this point it's it's just a standard way of solving your 2x2 system of equations, okay? And so whatever your favorite way to do that is, just by all means, just go ahead and use it, all right? Okay, so any questions on this before we jump to the answers? Okay. All right. And so if we solve the system equations, what we get is J1. J1, our first radiosity is going to be 19,277.14 watts per meter square. Okay. J2 is equal to 7708.93 watts per meter square. Okay. Right, and so now that we have J1 and J2, we can now compute the heat loss to the environment, okay? Right. And so in this case, what we want to compute is the heat loss from surface 1 and surface 2, right? And so this Q environment here is going to be a sum. Our first contribution is going to be Q1 infinity, okay? And our second contribution is going to be Q2 infinity, right? And so we can compute these just based on the thermal circuits, right? Right, and so Q1 infinity is going to be J1 minus J infinity, which is just sigma T infinity to the 4th, okay? Divided by 1 minus A1 F1 infinity, okay? Plus J2 minus sigma T infinity to the 4th, divided by 1 divided by A2 F2 infinity, okay? And so we plug, we have all the numbers for this that we have. And so what we get is Q environment is equal to 152.75.57 watts, just watts. Okay. All right. And so once you have the radiosities, it kind of unlocks everything for you. And so, then you'll be good to go. Okay. All right. So any questions on this? Okay. And so if there's no more questions, I have one more kind of small topic I want to go over. Since we're on this topic of radiation, I thought it'd be good to kind of close with this idea of environmental radiation. Okay. Right. Because in my opinion, I think no class on heat transfer is really complete without talking about how does the Earth itself get heated. Okay. And so that's kind of what we're going to spend this kind of last 20 minutes of this class for. Okay. All right. And so kind of like we talked about before, probably the most important form of radiation that we experience here on Earth is the radiation from the sun. Okay. And that's, the primary way that most living organisms on Earth receive their heat and their energy. Okay. Right. And so, even though, we're talking about the sun here, we can apply all the same concepts that we've learned about radiation, irradiation, and all that stuff. Okay. All right. And so, when you talk about, when we talk about environmental radiation, what we really mean is kind of the balance in between, the amount of radiation, the amount of heat that we receive from the sun, and the amount of heat that the Earth kind of radiates back into space. Okay. Okay. Because the Earth, it's definitely not nearly as hot as the sun, but it's also still a something that radiates heat. Okay. And so at the same time, while the Earth is receiving radiation from the sun, Earth itself is radiating the heat back into space. Okay. And so ideally, there should be kind of a balance in between these. Okay. All right. And so first, let's put some numbers on this. Okay. Or let's go ahead and quantify some stuff. Right. And so let's start with the sun. And so the sun, is really, really hot. And so oftentimes we assume the sun itself is a black body. Okay. And for the purposes of our calculations here, we're going to say that the temperature of the sun is 5,800 Kelvin. Okay. Right. And then also we know that the distance in between the Earth and the sun is 1.5 times 10 to the 11th meters. Approximately, right? And so we know that the Earth's orbit isn't perfectly circular, but on average, it's about this much. Okay. All right. And so because this is a very, very large distance, right? And because the Earth is so small compared to the sun, actually very little of the sun's radiation actually hits Earth, right? And so remember, we talked about this whole thing with view factors, right? So the view factor is just the ratio of how much of the radiation of one surface actually hits another one, right? Because the Earth is so tiny compared to the Earth, I don't have the numbers here, but you can imagine that the view factor between the Earth and the sun, so F sun Earth, right? I can imagine that number is really, really tiny. And so even though this sun is putting out all this heat into the into space, very little of it actually hits the Earth. Okay. And so in order to quantify how much energy actually hits the Earth, you can do a lot of calculations around this, but we're going to simplify a lot of it just because we only have just 15 minutes left. Okay. So any questions on this so far? Okay. All right. And so after a bunch of calculations, and I mean that, and so there's a lot of calculations that go into this, but we're not going to go into it. Okay. And so we can kind of boil it down into kind of one number, just kind of for the sake of our argument. Okay. And so this number we call the solar irradiation. Okay. And so the solar irradiation is the amount of heat from the sun that actually pierces the atmosphere. Right? Okay. And so this is usually the number that's usually useful for calculations on Earth, because this is, you know, this is actually the actual kind of heat that we feel. Okay. Right. And so in reality, you know, this is vastly oversimplifying this, because, you know, the amount of solar irradiation that you get depends on a lot of different factors. So it depends on, you know, where you are in the world, depends on the time of day, depends on the day of the year, depends on, you know, the atmosphere at the time. And so it's complicated. But just for the sake of this class, we can boil it down to one number. Okay. And so we'll call it GSO. Okay. And we'll say that GSO is equal to 342 watts per meter square, right? Okay. And so this is kind of the average heat flux that, you know, an average location on the Earth at the average time of day, at the average date of the year that it experiences. And so, you know, vastly oversimplified, but, you know, it'll do for our calculations. Okay. Okay. And so the way that we can model this is that, you know, we can say that the Earth is going to be kind of one big flat surface. Okay. I'm not advocating for the fact that the Earth is flat, because it's not, obviously, you know, no matter what people tell you online. Okay. But, you know, just for the sake of these calculations, we'll assume the Earth is one flat surface. Okay. And what we're going to say is that irradiating on the surface is going to be this GSO. Okay. And so this is going to be our 342 watts per meter square. Okay. All right. And so that's the amount of heat that the Earth is kind of receiving from the sun. Okay. Right. And so at the same time, remember, Earth is also emitting radiation. Okay. Right. And remember, any radiation that we give off, or a body gives off, we call that emission. Okay. And so Earth's emission, you know, we've also quantified this, you know, using very similar calculations. So, you know, depends on where you are in the world, time of day, time of date of the year, and things like that. But if we boil it down to just one number, it's about 390 watts per meter square. Okay. Right. Okay. And so, you know, by looking at this diagram, it seems like we have an imbalance, right? And so we have, you know, only 342 watts per meter squared coming in from the sun, but the Earth itself, it's emitting heat at a rate of 390 watts per meter square. Okay. And so it seems like Earth, you know, should be, you know, with these numbers, you know, the Earth is giving off more radiation than it receives. Okay. And, you know, and the way that we obtain this 390 is basically based on, you know, the temperature of the Earth and, you know, the Stefan Boltzmann constant and all that stuff. Okay. And so just purely looking at it just as a pure radiation problem, you know, we have the sun as a surface, we have the Earth as a surface, you know, two spherical surfaces. You know, it seems like we have an imbalance here. Okay. But you know, there's a lot of other factors that kind of complicate this balance. Okay. And to really fully understand all of these things, you know, you definitely have to take a course in, like, you know, environmental science and environmental heat transfer and all that stuff. And so we're just going to go over just very, very kind of high level details. Okay. But, you know, the main thing that kind of complicates these things is the atmosphere. Okay. And what I mean by atmosphere is kind of all the gases and all the chemicals that are in our atmosphere. Okay. Okay. Right? Because the atmosphere is filled with all these different gases, right? And so what the atmosphere can do, and it can do this for kind of both the solar irradiation and the Earth's emission. Okay. What the atmosphere does, at least in terms of heat transfer, is that it can absorb and scatter radiation. Okay. And so the actual diagram actually doesn't really look like this, right? And so actually what happens is that instead of 100% of the Earth's irradiation going to the surface, some of it actually goes into the atmosphere, right? Because as the, you know, as you know, as the solar radiation comes in, right? Even when I say the solar irradiation pierces the atmosphere, that's kind of piercing the outermost layer. Okay, but once you get past the outermost layer, there's still a bunch of like oxygen and nitrogen and CO2 in the air that can be absorbed. Okay, and so coming in, what we have is 342 watts per meter square. Okay, and about 67 of this goes into the atmosphere. And so that 67 watts per meter square doesn't actually usually make it to the surface of the Earth, okay? And so making to the surface of the Earth is kind of the difference in between these two, which is about 275 watts per meter square, okay? Right? And so the same thing happens on the emission side too, okay? And so on the emission side, some of it makes it back into space, which is good, okay? But actually a very large percentage of the Earth's emission actually goes to heating the atmosphere, okay? And so straight off coming from the Earth, the amount of radiation is 390 watts per meter square, okay? But actually going into the atmosphere itself is a huge percentage of this, right? And so a huge percentage of the 390, which is actually 350 watts per meter square, okay? 350 of that heat flux actually goes from the surface of the Earth into the atmosphere, right? And only about 40 watts per meter square actually makes it back into space, okay? And so a large percentage of the radiation that the Earth gives off never actually makes it to space. It all just kind of goes into heating the atmosphere, okay?
Is that the reason why for the greenhouse gases, because they have a high heat, or they're able to absorb a lot of heat then?
Yes, yes, yeah. So it's part of the problem. And so yeah, I mean a big part of the greenhouse effect and climate change and global warming goes into the fact that our atmosphere is kind of filled with a lot of these gases that absorb a lot of the radiation and doesn't let it go back into space. Yeah. And so actually, a big problem of climate change is the fact that our atmosphere just absorbs a lot of this radiation, and none of it, and not much of it actually makes it back out when it should be, in order to keep the thermal balance, nice and balanced. Okay. Okay. Any questions on any other questions on this so far? Okay. All right, and so as you can imagine, this is kind of a very delicate kind of balance, right? And so, even though I gave you numbers in this just to kind of give you a sense of what's going on, but in reality, these numbers here are changing, all the time, okay? And a big kind of determinant on how these numbers change is the chemical makeup of the atmospheric gases. Okay. And so, it's something that we kind of always kind of have to be careful of, okay? And so in general, and this is, again, vastly oversimplifying this. And so, it's a lot more complicated than this. And so the one that we have to worry about the most, and probably you guys have kind of seen this before, a lot of the, I think climate change is becoming a much bigger global issue, okay? And so a big contributor to this is carbon dioxide, okay? Okay. And so what's been observed is that as the content of CO2 in the atmosphere increases, okay, okay, what tends to happen is that the radiation that gets absorbed by Earth's atmosphere, okay, the radiation that's absorbed by Earth's atmosphere, this tends to move closer to Earth, to the surface of the Earth. Okay. And so as it's already given that the atmosphere is going to absorb a lot of the radiation. And so as long as we breathe oxygen and we spew out carbon dioxide from our bodies, it's not like we can avoid the atmosphere absorbing stuff. Okay. But what people are kind of generally worried about is that absorption of the Earth's emission, that's taking place closer and closer to the surface. Okay. And so what this will do, as that absorption gets closer and closer to Earth, this will cause the atmospheric temperatures to increase. Okay. Because if this absorption kind of takes place further away from the surface, that's generally more okay, because then that doesn't affect life on Earth. But as that absorption takes place closer and closer to the surface, that's going to raise global temperatures and lead to probably a bunch of issues that you guys have probably seen a lot in the in the last few years. Right? Right. All right. Question. So if we change the color of the rose to white, it would reduce the heat radiation. Yeah, actually, I've seen that. I don't know the specifics of that, but you can imagine that changing the color of something would definitely change its optical properties, right? And so since radiation depends a lot on the optics, changing that color would definitely have a big impact on that. Yeah. Mm-hmm. All right. And so just kind of as a parting kind of comment here, so CO2 is kind of the big thing that we have to worry about, and so. This affects a lot of our work as engineers, because a lot of times we design systems, manufacturing processes or vehicles that can emit a lot of CO2, right? And so part of our responsibility as engineers going into the future is to try to minimize this impact as much as possible, right? And so understanding how your processes, how your vehicles, how they emit carbon, and how that affects this global radiation balance is, it's a big part of thermal engineering, right? And it's even it affects everything kind of on a global scale. Okay. And so as we start to improve, our engineering processes, as we get more clean, we get more efficient, right? That's going to lead to kind of better, a better kind of overall global climate. And engineers are going to be central to that, because we're going to have to be the ones that develop those technologies. Okay. Okay. So any final questions on this? Okay, so that's all we got time for today, and so thank you guys for tuning in. And so Wednesday we'll have our review, all right, and then that'll be our last class session, right? So thank you guys for tuning in. Hope you guys have a good rest of your day, and I'll see you guys on Wednesday.
Thanks, Professor.
Thanks, guys. Would that cause more snow blindness on the road? I think yes. I think that's probably a big concern, is that it would reflect the light, and people would be blinded and have more car crashes. Yeah, I'm sure that's a huge concern.
Thank you, Professor. I have to get going.
Yeah, okay. I'll email you back your question, Nicholas. Yeah.